I think we talked about that when we were talking about like different, like different, when we were talking about the enzymes that certain viruses carry in their core, that was one of them, reverse transcriptase, which basically transcribes from RNA to DNA. So it's like backwards, right? Okay, so HIV, human immunodeficiency virus, is a retrovirus. It attacks the cells of your immune system, which are basically like your T cells, right? Which are the ones who are supposed to like defend you, right? So it's really dangerous. That's what makes it so dangerous, because you can't produce enough T cells in order to like combat the, you know, the attack on the T cells from the virus, right? And do you guys remember what were opportunistic infections?
They like start to come about when they see that your immune system is weak, so that they like take over.
Exactly. So once your immune system is kind of like weakened, they sort of like, you know, come in and like take advantage of the situation and like kind of kick you when you're down, right? So they like under normal circumstances, they wouldn't be able to get like a foothold, but once you're kind of weakened, they can come in and attack. So no one ever actually dies of AIDS or HIV, but they do die because the HIV and then later stages of AIDS like weaken their immune system totally, so that like other things can easily, you know, take advantage of it. Like pneumonia, right? Most people typically, like, you don't die from pneumonia, right? Like you can, you know, you can recover from it, but because their immune system is so weak, they can't, right? So a lot of times someone who has AIDS might die of something like seemingly harmless, like pneumonia or something, right? Sorry, this is really graphic. I should have warned you earlier. So here's a model of what the HIV virus looks like itself. So here's the core, here's the capsid, right? And here's like the, you know, the envelope. And then this is really, I'm sorry, this is really disturbing, but this is basically, it's a type of cancer, skin cancer, that is common in HIV positive patients. And again, it's like a type of opportunistic infection, right? Because, you know, the HIV isn't causing this, but HIV weakens you enough such that, you know, that you're susceptible to these other conditions that that can creep up. Okay. All right, Ebola, that's another one that's been a big problem in recent years, right? There was like a, you know, there have been outbreaks. And it's highly contagious, right? So even when you're throwing away the bodies, like it's transmitted through bodily fluids. So like even when you're throwing away the bodies, it's like still really, really harmful, right? Or like contagious. So, and this is sort of what the virus looks like. And it can still be transferred to the people. So it has a 50% fatality rate, which is very, very high, right? Okay. Excuse me. So measles, right? Have you guys seen, you haven't seen anyone with measles, have you? I hope. No. There's the MMR vaccine, the measles, mumps, and rubella vaccine, which there's, you know, it's like regulated. You have to take that, right? Unless you have like some medical condition, or unless you have like a religious exemption, like you really strongly don't believe in, you know, vaccines or whatever. But basically, this is also caused by a virus, right? And it causes, you know, like these little bumps that are itchy. So yeah, so measles is another virus-caused disease. Herpes, have you guys heard of herpes? Yes? No? No? All right, well, herpes is also caused by a virus. It can be, there are two different types of herpes. There's herpes simplex 1, which usually affects like your mouth, right? And then like people who get cold sores, usually it's like when your immune system is down otherwise, this virus then creeps up into your nerves. It hides in your nerves, and then it causes like a, you know, like an eruption. So like a lot of people get herpes, cold sores on their mouths, right? And then, so like that, right? And it's very contagious, not only when someone has a cold sore. So like, obviously you shouldn't ever like come in contact, you know, with your lips with someone else who has like a cold sore, you know, at that time. But you can be contagious even when you're not actually like having an outbreak. So herpes is like actually one of the most common It's incurable, but it's not like deadly. It's not going to kill you. But it's very like unsightly, like, you know, when people have a cold sore. And it's actually like more people than you'd think. 2 out of 3 people under the age of 50. That means like 2/3 of us. So if there are like 19 of us in here, right? Like 2/3. So that's like more than 12 people have herpes in their, you know, in their systems. That's kind of scary, right? But in any case, herpes simplex 1 is usually, you know, around the mouth. But there's this other version, which is sexually transmitted, which is called herpes simplex 2, which obviously comes, you know, can be spread through sexual contact. And even you can also spread herpes 1 to someone else's genital area. So you should also be very aware of those kinds of things. So it can still be contracted like by any sort of like direct contact. So this is, but again, it's not going to kill you, but it does. You have these like periodic outbreaks where you either get a cold sores or like blisters, and you know, apparently it can be very painful and, you know, unsightly again. So that's another one. Norovirus, right? This is like kind of interesting little pictorial thing. But norovirus, again, it causes like gastrointestinal problems, like or vomiting or diarrhea, right? So that's another type of virus that you guys might be familiar with. Rotavirus also, noro and rotaviruses both typically affect the gastrointestinal tract and then cause vomiting and diarrhea, right? Have you guys heard of noroviruses or rotaviruses? Sort of, yeah. All right. And then rhinovirus, this is, it's made of RNA. This is the typical common cold virus. And there's so many different strains of them. That's why people get colds. And then even though you've had a cold before, you still can catch another cold because there's all these different types of them, right? So rhinovirus, I always think of rhinoceros has like a horn on their nose, and then think of like a cold, like affecting your nose. So in any case, and this is actually the most common viral infection of all, right? Because it's like, you know, constantly people are always getting colds, right? And then have you guys heard of hepatitis ABC? You probably have been vaccinated for hepatitis B, definitely, right? Or A, I think, you know, there's certain, you know, they're all kind of related, but they're all caused by a virus, right? And they actually, like, the virus affects your liver, right? And it can cause a lot of damage to your liver if it's not like, you know, yeah, if you get it. So you need to get a vaccine to prevent it from happening, right? Okay. Are you guys all still following me? Yeah. And then HPV. Have you guys all heard of HPV? It's also, it's what's it called? It's caused by a virus. It's also a sexually transmitted disease, and it can have symptoms or it can have no symptoms. And that's what's kind of scary about it too, because, you know, it can cause like genital warts, but it can also not cause them, or it can cause them like sort of more internally. So it's kind of scary, and it can cause cancer to develop. So it's, you know, there's a vaccine for it now. When I was like younger, they didn't have a vaccine for it. And the vaccine is also like very controversial. A lot of people don't want to get it because they don't want to like even admit the possibility that their child could be sexually active. So they don't, you know, they say like, oh, well, my child wouldn't need it because they aren't, you know, but so there's kind of like a stigma against it still. But this is actually, you know, it prevents you from getting, you know, cancer. So I don't know. I think in this video that I'm going to have you watch tomorrow, you can kind of see the support for it. But anyway, so HPV, there's an HPV virus, right? That's caused by a virus too. So do you see like all the different like crazy, not crazy, but like the really, really wide variety of viruses that are like, you know, we're basically being, you know, attacked, or like we have the threat of all these different viruses like at any given time. So it's really important to, you know, wash your hands, be safe, right? Not engage in certain activities that could, you know, raise your chances of getting any one of these, right? Okay, that's enough preaching for today, right? Okay, so testing for viruses. So we said that certain of Koch's postulates, they actually can't, they can't be, you can't grow a virus on a culture, right? Do you guys know why?
It needs a host, so you don't know if it's affecting the host or the virus itself.
Exactly, right. The virus needs a host cell, right? And can you just grow any types of cells like on a little like plate? Like, and does anything just grow on a plate by itself? So there's like it's a very like delicate procedure to grow tissues on on a plate. And suppose they're human cells. Suppose we're studying a virus that like affects humans, right? Is it ethical or like accepted to just like go ahead and grow human tissues like on a plate in a lab? First of all, it's very, very difficult to do that. But even if it were, completely possible, can you just like grow someone's like, grow a heart to then test a virus's effect on this heart? There are a lot of like there are ethical and logistical factors that don't let you just do the Koch's postulates and like grow them on a thing and then reinsert them back into a test animal or something. So we need to figure out other ways to test for viruses, right? So one of the ways is to test for antibodies, right? Do you guys know what antibodies are? We haven't done the immune system yet, but basically antibodies are proteins that are cells make that attach to specific like virus particles, right? To sort of like neutralize them, right? So they can't bond to receptors on our cells anymore, right? You can also test for antigens, and antigens are the parts on the virus themselves, right? So you can test for antibodies, which are produced by our own immune system. You can test for the antigens, which were on the virus itself to begin with, okay? Or you can also make a viral culture, but again, the challenges to that are like really, high. So you need to, obviously you need to, take that into consideration. So it's not always a possibility, right? And then another way you can do it is to look for the viral DNA or RNA itself. So now that we can sequence all this stuff, we can know which sequences are human sequences and which sequences are foreign sequences, right? So that might help us also figure out what a virus is and if someone has it, right? I want you guys to look at this video real quick, and they're going to show you these different techniques of like how to test for viruses, right? There's one called a Western blot, and then there's one called an ELISA test. And I want you guys to just watch this real quick and see if you can. Is this it? Yeah. Okay, so let's just watch this real quick. Can you hear that? Is it muted?
I can't hear anything.
I can't hear it either. Here we go. Oops.
Oh, today we're in the life sciences laboratory.
Can you hear that now, kind of?
Yeah.
Some of the techniques we can use to determine if somebody's suffering from or has recently suffered from a virus. Student Katerina Hartman and researcher Dr. Lisa Bishop will be joining me to do some of the demonstrations. The first technique we're going to look at is Western blotting, which was developed by W.A. Burnett in Seattle in the 1980s, based on earlier work by Ed Southern. Western is a triple play of words referencing Southern, the first initial of W.A. Burnett's name, and also the geographical location of the city of Seattle. So Katerina, what does Western blotting involve?
In the Western blotting, we use a thin gel which we place in a tank of buffer solution. Then we put the serum samples from the patients into the top of the gel and apply an electric current. The sample then flows into the gel, and the protein from the serum are separated according to their size.
What does that remind you guys of?
Gel electrophoresis.
Excellent, good. Oops. Wait, why is it not pausing? All right. Sorry, hang on a sec. I'll stop doing that. Okay, here we go. All right.
Larger ones run slower and smaller ones faster.
Katerina is now loading the gel. the gel's been running for a while now, and the blue dye's nearly reached the bottom. So what happens now then, Catherine?
Once the gel has run to the bottom, we're ready to remove it from the tank. It's then laid flat and a nylon membrane is placed on top of it.
So the proteins are drawn out of the gel and onto the membrane. Is that why we say it's blotting?
Yes, and the proteins are then fixed in place and available to interact with the antibodies. If we have an antibody to a certain protein, we're able to determine if that protein was in the serum sample that we ran on the gel.
So, Katerina, how do we know that the antibody has detected the protein?
Well, the antibodies are themselves proteins and can interact with other antibodies known as secondary antibodies.
So that's quite complicated. We have an antibody that binds to a protein, and then we have another protein, another antibody that binds to that antibody.
Exactly, and that secondary antibody has a chemical group attached to it that we can develop to show some color, like a photograph in the old days before digital cameras.
Ah, yes, I remember the old days before digital cameras, even Katerina doesn't. Katerina is now performing the reaction that develops the colour in the membrane. So, Katerina, we're now looking at the results of the Western. So what do the results show us?
So we can see here that these lanes are negative. There's nothing in them, but these other lanes here have bands in them.
Right, so that means that the patients corresponding to the lanes that have bands in them do have viral proteins in their blood, but the others don't.
Yes, and we also expect that these bands here to be a certain size, corresponding to the size of the viral proteins we're looking for. But if the bands are the wrong size, we wouldn't assume that we had a positive result, but we would need to do further testing.
So we've just seen Western blotting, which directly detects the presence of protein in the serum sample. So a positive Western blot result would indicate that the patient in question was either suffering from the virus or incubating the virus at the time the sample was taken. So Lisa, we're going to look at a different technique now called ELISA. What does ELISA stand for?
ELISA stands for Enzyme-Linked Immunosorbent Assay. It's different from Western blot because in the ELISA, we're looking for antibodies to the virus rather than the viral protein itself.
Right, so it's actually the response to the virus rather than the presence of the virus that's been detected.
That's exactly right. So the ELISA will give us information as to whether the patient's seen the virus in the past.
And of course, by the time we do the ELISA, the patient may have recovered from the virus. And so Western, which is the other technique would actually be negative. So the virus would tell us about the past experience in patients.
Yes, exactly.
So no gels needed then for the ELISA technique, Lisa?
No. The first thing we do is incubate the serum from the patient with a viral protein, an antigen. This protein acts as an immune challenge to the antibodies in the patient's serum sample. If the patient has antibodies to that virus, they'll bind to the challenge proteins.
Lisa is now setting up the ELISA. Secondary antibodies are used again, but because there is no gel, unlike the Western, we have to read the output of the colour development reaction using a spectrophotometer.
I think it's supposed to be muted there, or did I just mute it? No. Okay, there we go.
So now we're reading the results of the ELISA plate that we set up earlier on. So what did the results tell us then, Lisa?
Well, the colour and the number correspond to the optical density of the sample. So where the number and colour are strongest and highest, it's an indication that the patient has a lot of antibody to that particular viral protein.
Right. So the patients that have got higher numbers here are the ones that have been exposed to that particular virus at some time in the past, and they now have antibodies to that virus. Whereas the patients here that obviously have much lower numbers, in fact, in some cases quite close to zero, these are probably patients that have no antibody, which would mean that they're patients that haven't been exposed to that particular
That's
virus.
exactly right.
All right. Do you guys understand what was said? Sort of. Is it hard? All right, let's go through each one. And I actually want to do this one first. All right. Okay, so are you guys still with me? Yeah? Okay, so what happened in a Western blot again? So the Western blot, did it have a gel or did it have just like those little wells?
I had a gel.
Okay, it had a gel. And so what they did was they took samples of patients' blood, right? And then they ran it through the gel. Presumably the patient's blood would have, what are they looking for in the patient's blood?
If they have the viral proteins.
Exactly. They're looking for the antigens, right? The antigens are the viral proteins, right? And they're separating them based on like size and charge, right? And so again, they run the mixture through there, and then the larger ones are going to travel the slowest, and the shorter ones are going to travel the fastest, just like a gel electrophoresis, right? And then they take the gel, right, and they transfer all the proteins that have been separated through that gel. They transfer that to like this paper, like nylon membrane thing. They just like basically like press it against it, and they all get transferred to this membrane. I'm not sure why they have to do that part, but they transfer it to this nylon membrane, and then they apply antibodies, right? So they know which viral proteins they're looking for, and they already have antibodies to that viral protein. So let's say like it's rabies, right? We're testing for rabies. So the rabies antigens, like the rabies viral particles, are going to be in that, on those little bands of the gel, right? And then they're going to be transferred to the membrane. And we took rabies antibodies from some other animal that had the antibodies, right? And we attach we apply that to the membrane. And if they attach to something on the nylon membrane, how will we know that? There's a way to detect if those antibodies bind to the ones on the membrane. And if they do bind to the ones on the membrane, usually it's like some sort of like color change, or it could be some sort of like fluorescent like marker. But in any case, they can tell whether those antibodies have bound to those ones on the membrane. And if they did bind to the ones on the membrane indicated by some sort of marker, then what can we conclude? That the patient has what in their blood? We can conclude that they have those viral antigens in their blood, right? So there's going to be some sort of marker attached to the secondary antibody, right? But the first antibody is the one that's going to attach to the antigen. Are you guys all with me or no? Yes? What happens if this patient had been exposed to the virus, but then like recovered from it? Will they still have viral antigens in their system?
They won't have the antigens, but they'll have the antibodies.
Exactly, right? So that's why we can't use this to test for someone who's already had it a long time ago, because the viral antigens will be gone, right? So what kind of patients can Western blot test for then? People who either are currently experiencing an outbreak, or like are being, who are currently suffering from this viral disease, or people who are incubating it. So like they're not sick yet, but they already have the virus in their system, right? Whereas the other technique, what was the other technique called again?
Wait, would carriers be there incubating it or no?
Well, it depends. So if the carrier, if they have it, if they recently got it and then they haven't gotten rid of it, then yes, they would test positive for this.
Like even if they didn't show any symptoms or anything?
Right.
Okay.
Yeah. Okay. So then so again, it's kind of like a weird thing, and I don't know why you can't just put a marker on the first antibody, but it's like, so basically the original, like the protein, the nylon membrane will have proteins, the antigens on it. The antibody will connect to those antigens, and then you have a secondary antibody that's going to have a marker on it that will connect to the first antibody, right? So it's like 3 different layers. Do you guys see those 3 different layers on here? With the original layer, the one, you know, like the one on the membrane being the antigen, right? Okay, so ELISA, sorry, the drawbacks of this, let's just go through the drawbacks real quick. This is more expensive to do than the Western blot, than the ELISA. And it's also very labor intensive. You have to keep like, you know, run the gel and then transfer it to the membrane. And then you have to like put on the antibody, then you have to wash it again and then put on the other antibody. You know, it's very labor intensive. So it's not like totally ideal. And also it won't detect an older, it won't detect someone who had been exposed and then has gotten over it, right? So that's why typically ELISA is preferred, right? ELISA stands for enzyme-linked immunosorbent assay, right? So it's like ELISA, right? And so basically what you do is you start with that plate, right? With all those little little wells in it, right? Those little like sort of like holes, right? That you can put the liquids in. And sometimes it's like, you know, they're like you know, a lot of those little wells, and they have those like pipettes that have like, you know, like 10 different like things at a time that you can insert. But basically for ELISA, instead of testing the blood for the antigen, you already have the antigen. Like we know what we're testing for, and it has to already be in the plate. So when you first buy an ELISA plate, you buy it for a specific virus, and the virus antigens are already installed in that plate on the first layer there, right? And then after, so suppose I say like, you know, I want to test, you know, these patients' blood for HIV antibodies, right? So I go and I put the HIV antigens, or the HIV like particles basically, on the bottom of the tray. And then I fill the tray first with the serum from the patient's blood, right? And what would I expect if they have HIV, or were exposed to that at some point? What would I expect to be in that blood then?
And
What would I expect?
you would have antibodies.
I would expect antibodies to be in there, right? And then what will antibodies do if exposed to that tray with the HIV antigen in it? What do antibodies do to antigens again?
They like fight them, kill them.
They attach to them, right? So they bind to them. So if I have a tray that has HIV on it, and then I put a patient's blood in it, and the patient's blood has HIV in it, has been exposed to HIV and has formed antibodies, those antibodies will bind to the HIV on the tray, right? And then again, in this process too, you also have to use a second, antibody that has a marker on it. In this case, sorry, I went through this already. You have to wash it every time you apply the new antibodies. But then once you add the second antibody, that second antibody has an enzyme attached to it, right? And when you add a substrate to an enzyme, what happens to them? Enzyme and substrate, the enzyme facilitates some sort of reaction to happen, right? So then we're going to wash it again, and then the enzyme will have stuck to the antibody, and that means the color will change when the substrate is applied. Are you guys following me, sort of? No? Let's see if this video helps. I think it helps a little bit. But, okay, here we go. Is it this one that I wanted to? I think it might be this one. Okay, oops, sorry. Are you guys, why can't I do this? It won't let me like close it. close this kind of thing. Okay, so do you guys see how the tray, this is the well, and it came originally with the antigens for that specific virus, right? So these are the HIV, let's say like antigens, right? And then they add this serum, right? And this is like the patient's blood, basically. And if there are antibodies in there, they'll bind to those antigens, right? Are you guys all following? Okay. So they bound, right? You can still see it, right? So now they add these secondary antibodies, and do you see those secondary antibodies have an enzyme on them, right? So the first antibody, here's the second antibody. These second antibodies have the enzyme on them, right? And then if we add the substrate to that, we wash it again, obviously. And then when we put the substrate on there, if the enzymes are still there, meaning they bound to the other antigens, that means that there will be a color change in the overall reaction, right? And then you put it in a spectrophotometer to read the color change, and then you can detect which ones had the antibodies and which ones didn't, right? Do you guys see that? So suppose there are no antibodies, right? And we put the enzyme linked secondary antibody into this well, right? And then we washed it. What would happen to the enzyme if we washed this all off and there were no antibodies there?
The overall thing wouldn't change any colors.
The enzymes would have been washed away, right? So then when we add the substrate, the overall color wouldn't have changed, right? Okay. All right. Are you guys still there? Okay. Hold on. Hold on 1 second, please. Get out. You have to get out. No, I told you not to come in when we're doing class. Shh. No, you cannot. No, get out. Don't stop. Don't stop. You guys need to, I'm sorry, we're still doing class right now, okay? You guys, we talk about this every day. Go out now. Now. Rena, out. Out. No. Ready? Don't stop! Don't stop! Hey, you're too loud. Stop. All right, are you guys still there? Okay, hello?
Hello.
All right, I'm sorry. My husband was like outside doing annoying stuff in the garden and not watching the daughters. And then they stormed in like demanding to watch like something on TV, and I don't want them to watch anything on TV right now. Okay, so here, so you guys kind of get a better picture of it after seeing that video? Yeah? Okay, so basically if you buy the tray that has like the antigen already in it, you add the patient's serum, right? Then you add another secondary antibody, and then you add the substrate. And then if there's a color change and you measure it on the spectrophotometer, then you know that the patient has been exposed to that at some time. Will it tell you if they're currently if they're currently being attacked by it or they're currently suffering from it? Will those results tell you if they currently have the virus or no?
No.
No, they'll only tell you about the history of it, right? Whereas the Western blot will tell you if they're incubating or if they're currently suffering from it, right? Okay, the drawbacks to this, basically, you need kind of a larger sample of, so like if someone's like just recently gotten an infection and then, just recently, been exposed to the virus, they might not have built up enough antibodies yet. And so then the antibodies might not be detected in the serum yet, right? Because they don't have enough antibodies. So that's like kind of one drawback. And another one is that you have to know the virus, right? Because in order to like test to see if someone has HIV by the ELISA test, you need to put the HIV, you need to get a tray that has the HIV antigens already in it, right? So that's another sort of drawback about that technique, right? So this is like the second way. Just make sure, you know, and make sure for our purposes, we're just going to say that the Western blot test for the antigens and the ELISA test for the antibodies, okay? But actually, there are some cases where ELISA tests for antigens and Western blot tests for antibodies too. But for our purposes, just try to remember that. And then there's this new method. Actually, I like read about it last year, and it's like, I think it was in the University of Colorado State University. And do you guys see this wire here? Do you see this like little, like really, really thin little piece of wire here? So basically what that is, it's really sensitive, and it you put these viral proteins, you put the viral proteins on the wire. So instead of putting it in the bottom of the wells in the ELISA, somehow you can get the viral proteins or the antigens on here, and then you dip it into like, you know, some sample that will or will not have antibodies. And if it has the antibodies will bind to those viral proteins on here, and then this will have more mass and more charge if the antibodies are on there, right? So for those tests like ELISA, which aren't very sensitive, this would be really good because you could detect even like a small amount of antibodies based on the weight and the charge difference on this wire after you dip it in the antibodies, right? So that's like really cutting edge. It's kind of cool. I thought that you guys should know about that technique, right? And the last one is that the viral culture idea, right? Remember I told you about this? And again, you can add the virus to cells that are growing in the culture, but again, there are certain ethical considerations and just like logistical. Like it's not always easy to just grow some cells on, you know, on a plate. And, you know, if they are human cells, and then you're just kind of like exposing the human cells to this virus, it's, you know, it's a little questionable, right? So there are problems with this technique as well. Okay. All right. And then this is like the last technique, but basically, if suppose you don't even know what a virus is, can you do an ELISA for it or no?
No.
You can't, because you don't know that, you know, you don't know the composition, you don't know the sequence, like what the, you know, so clearly, you know, you need to be able to have a method to detect like viral DNA, even if you don't know what the virus is. And the way that they do it is basically, and this is used for new viruses, they look for your viral genome by subtracting your known genome from this whole, so suppose we think we have a cell that's infected, right? And maybe it's infected with viral DNA, and maybe the virus is like going through the lysogenic cycle, so it's kind of inserted its DNA into some other, so its host genome, right? So what you do is you take the cells that are infected, you think, right, and you sequence their DNA, right? Or you can do it by sequencing their RNA, like mRNA, right? And then you take normal cells and you compare, you basically subtract the normal cells from the infected cells, which would presumably have the normal cells' DNA and the viral DNA in them. And so if you subtract this from this, what will you get? Anyone?
The unknown cells?
Exactly. Not the unknown cells. You'll get the viral DNA, right? So if this cell, these infected cells have like all this DNA, and we subtract all the normal DNA from, you know, those infected cells, then the rest, the leftover, anything that wasn't subtracted from the normal cells is basically the virus or the viral DNA, right? Do you guys have any questions? No? All right. Does this all make sense? I think that's it. Okay. So, where are you guys? Okay, here. All right. No one has any questions? You guys understand what about viruses? Do you think you need a quiz on viruses to like make you learn it, or do you think you're okay with just doing? We'll do a short lesson tomorrow, and then I'm going to have you guys watch this video, and then answer a few questions to the video. Does that sound okay for our virus unit? And then we'll start fresh next week on what are we doing next week? I'm trying to, oh. No, okay, yeah, next week I think we're gonna start fungus. We're gonna do fungi. No, we're gonna do protists first and then fungi. We're only gonna spend like a day on each of them just because I don't think, you know, like a lot of it was like microscope work, and then you guys can't really look through the microscope and do it for these. And there's like this protist project where you like are supposed to research all these different protists, but I don't think I'm gonna make you guys do that. We're gonna just go over protists, fungi. Then you guys are gonna do the disease. You're gonna like research some diseases. Okay, does that sound okay? Yeah? Good? All right. Have a wonderful day, guys. I'll see you tomorrow. No homework for tonight, all right? Just make sure you finish, you know, if you didn't do the virus thing, make sure you finish that up. All right? And I'll see you tomorrow, okay?
Have a
Bye. Thank you.
All right, bye, guys. Bye.